Hi students, in this video we are going to discuss about energy. Now, what is energy? You know what is energy, isn't it? It is the ability or capacity to do work. If you have more energy, then you can do more work. If there is less energy, then you can do only less work. So energy is equivalent to, in a sense we can say it is equivalent to work. Now, like, since energy is work, we can say like work, energy is also a scalar quantity. Its unit is either Newton meter or joule, and its dimension is n square t raised to minus 2. Now, in lower classes, you have studied different forms of energy, isn't it? So, different forms of energy, light energy, heat energy, kinetic energy, mechanical energy, chemical energy, etc., etc., etc. Now, in this chapter, we are going to mainly study about mechanical energy. Mechanical energy. Now, what is mechanical energy? It is as energy processed by the body by any mechanical means, by any physical labor. The energy obtained is mechanical energy, and it is of two types. First one is kinetic energy, and second one is potential energy. So we have mechanical energy into two, that is kinetic energy and potential energy, of which in this video we are going to discuss about kinetic energy. What is kinetic energy? What is kinetic energy? It is the energy possessed by an object due to motion. Energy obtained by my body due to motion. Energy in a body due to motion. What we call kinetic energy. Now, we are going to derive the expression for kinetic energy using calculus method, that is integration method. So, kinetic energy using calculus method. For that, what we are doing is, I told integration means first it is finding the total effect. So in this case, first we will find out the amount of work done in displacing the object through a small distance. Then we will integrate and find out the net work done, which is equal to the energies of the body. So imagine there is a body of mass m, which is initially at rest, which means u is equal to 0. Let the force F be applied on the body. What happens? The body starts to move and attains the final velocity v. Right? Initially, the body be displaced through a small distance ds. Okay? So, upon applying the force, the body travels through a distance ds. Then the small work done in moving the body through distance ds is dw is equal to f dot ds. Here we are assuming that the body is traveling in the direction of applied force. So theta will be equal to 0 degree. So this can be written as f ds. Now, according to Newton's law, we know that m is equal to what? M is equal to, sorry, according to Newton's second law, F is equal to what? F is equal to m into a. So, according to Newton's second law, F is equal to m into a. So we can write dw is equal to m a ds. Now I'm going to write a in terms of velocity. We know acceleration is rate of change of velocity. So this equation can be written as m dv by dt into ds is equal to, I'm going to divide ds by dt. So I'll get m ds by dt into dv, which is equal to mv dv. So the small work done in displacing the particle through distance ds by using force F is mv dv. Therefore, the total work done to change the velocity from its initial value 0 to final value v is w is equal to integral from where to where I am changing my velocity from 0 to v dw, which is equal to integral from 0 to v and v dv. Now, m is a constant, I can take it outside. So m into integral from 0 to v dv. I am integrating my equation with respect to v. That is why I am writing dv. So v raised to 1. When we integrate, what will we get? V raised to 1 plus 1 divided by 1 plus 1. That is v square divided by 2. So I can write this as equal to m into v square by 2 with the limit 0 to v. Now this and we will be having a value like 25 meters per second, etc. So you can substitute it and find the final work done. So this is equal to m into upper limit, that is again we have written it as v itself, minus lower limit. Or at the end we can write the work done as w is equal to half m v square. So this work done is equal to what? Is equal to kinetic energy of the body. So we can write kinetic energy denoted by K is equal to half m v square. So the kinetic energy of the body is half m v square. Next, we are going to derive the relation between momentum and velocity. We know that momentum is denoted by P and that relation with mass and velocity is P is equal to m into V. And kinetic energy is given by K is equal to half m V square. What I am going to do is I am going to divide the right hand side of this equation, divide and multiply the right hand side of this equation with m. So I will get this as half m V square into m divided by m, that is half square v square by m, which is equal to 1 by 2m into m v the whole square. Now what is mv? It is the momentum, so this can be written as k is equal to v square by 2m, or momentum p is equal to root of 2m into k. This is the equation connecting the kinetic energy and momentum of the particle. P is equal to root of 2mk. So its kinetic energy is given. You can find a momentum. Momentum is given. You can find kinetic energy using this equation. Next, we are going to derive the relation between work and energy. It's known by the name work energy theorem. Work energy theorem. Now the theorem states that the total work done by the force on a body is equal to the work done by the force in displacing or in moving the object is equal to change in kinetic energy. The work done is equal to change in kinetic energy. Now, we are going to prove this theorem. For that, consider a body. Consider a body of mass m having initial velocity u and final velocity v. Okay. So there is a body having initial velocity u and final velocity v. Now this derivation is similar to the derivation of kinetic energy. Only difference is that here we are taking the value of initial velocity of u itself and not 0. Okay. And let F be the force applied on the body which makes the body move through a distance ds. So the amount of work done by the force dW is equal to F dot ds is equal to F ds, since we are taking F and ds along the same direction, and by applying Newton's second law, F is equal to ma, we get dW is equal to ma ds is equal to m of a dv by dt into ds is equal to what? M ds by dt into dv, which is mv dv. Okay, so we found out the small amount of work done by the force in displacing it through distance ds. And what is the next step? Total work done. Total work done in changing the velocity from u to v. How will I find the total velocity? We have to integrate. dW from where to where? I have to integrate from initial velocity to final velocity. So it's equal to integral from u to v mv dv. M is a constant, take it outside, v dv will become equal to what? Integrating, you will get v squared by 2 within the limit u to v. Now, how to apply the limit? Equal to m by 2 v square within the limit u to v. How will I apply the limit? It is upper limit minus lower limit. So, m by 2 into upper limit, that is v again, minus lower limit is, instead of v, you want to have right u. So, this can be written as half m v square minus half m u square. This is equal to final kinetic energy, denoting by k suffix as f, minus initial kinetic energy, that is k. So, work done is equal to what? Change in kinetic energy. Hence, the theorem is proved. I hope this method is clear to you. You have to study calculus method itself when you are deriving the expression for kinetic energy and also for work energy theorem. Thank you.